everyone, my name is Aiyani Hadfina Binti Azmi, and today I'm going to present for my mini project for EEP 208 Electrical Power Technology. And my project title is Three-Phase Wire-Connected Generator, Transmission Loss and Load. First thing first, we look into introduction. As we know, a three-phase system can be connected in two ways, which is in delta connected and also in Y connected. However, in this project, we will be focused on Y-connected generator and load only. There are two types of Y-connected in three-phase system, which is three-phase 3 wires and three-phase 4 wires. For the three-phase 4 wire system, it includes the neutral line, which can be ignored if the load is balanced. In Y-connected system, we know that E line is always greater than E phase, while I line will be equal to I phase. As you see in the slide, E line is equal to Z3 of E phase, while I line is equal to I phase. And then according to the Electricity Supply Application Handbook B3, the limits for the voltage drop for 275 kilovolt is plus minus 5%. So I was given a V line of 275 kilovolts. So my limits for voltage drop is around plus minus 5%. And this is the equation to calculate the voltage drop in percentage. And next, the power factor for the 132 kilovolt and above is 0.9. Also, this value of power factor is given in the book. Next, the power consumed by the load can be calculated using two methods, which is 2 wattmeter method and conventional measuring method. There are three objectives of this project. The first one is to evaluate the parameters of the three-phase system, and next, to analyze the differences of value from the calculated value and the simulation value, and the third one is to justify the normal operating condition for the system. And next, we look into methodology. So firstly, the value for V line and also transmission and load impedance is assigned to students, and this value is given based on our metric number. And for the power factor value and the limit for voltage drop is given from the book. And next, we have to calculate the parameters of the three-phase system, which is I line, I phase, and V phase, and also the percentage of V drop and the power consumed by the load. And next, we have to do the simulation using the PCM software, and this simulation is to prove whether our calculation is correct or wrong. And next, we have to compare the simulation value and also the calculated value. And this will help us to identify whether is there any differences in calculated value and also in the simulation value. And next, we look into findings and discussion. The first one, we will look into results. So these are the calculations. First, we are given the V line. For me, I received 275 kilovolts. And then given the values for transmission and load impedance according to metric number. And then by using V line, I can calculate V phase using this formula. V line equals to Z3 of V phase, and I'll get 158.77 kilovolt. Next, since the load is balanced, so we can ignore the neutral line. So the current flow in the neutral line is equals to 0. And next, we can calculate I phase using the V phase we obtained earlier, and also the total impedance, which is the impedance of the transmission and also the impedance of the load. And then we get this answer. Since this system is a balanced load, so the value is almost the same except for the phase angle. And next, for Y-connected system, we know that I phase is equal to I line, so I phase that we get earlier is equal to our I line. And next, to calculate voltage drop, we have to find V load first. So V load is equal to I phase times with Z load. So I phase times with Z phase, we will get this value, which is 149.44 kilovolt. And then we can calculate the voltage drop, which using the equation from the book, V supply minus V load over with V supply times with 100 because we want the value to be in percentage. And then I get the value, which is 5.88%. So this means that my system is good. And next, to calculate the active power, first one we use 2 wattmeter method. So the equation must be derived first, which is for the wattmeter 1 and also for the wattmeter 2. As we know, the equation for power in three-phase system is equals to VI cos and the angle difference between V and I. And this is also equal to V line times with I line and also cos phase angle between V and I. So to find the phase angle, we use the phasor diagram, which is this one. We draw it first. So the first angle we need to find is the angle between VAC and IAA. So VAC is here and IAA is here. Assume IR as IAA. So we get the angle between this one. So 30 minus with this angle. So we'll get this 30 minus the angle, which is we call as 5. And next we want to know the second angle, which is the angle between VBC and IBB. So VBC is here and IBB is here. So we need to add 30 degree here with this angle. So 30 degree plus with 5. So substitute this value in the equation I mentioned before, in this equation. So we will get this final equation for wattmeter 1 and wattmeter 2, which is wattmeter 1 VLIL cos 30 degree minus 5, and for wattmeter 2 is VLIL cos 30 degree plus 5. So since the power factor can be obtained from the book, so we can know the angle, which is the 5. So power factor equals to cos theta, and the phi is equals to 25.84 degree. And next we substitute the value for V line and I line and also the phi. We'll get this answer for wattmeter 1 and then for wattmeter 2. Then we add the both value and we will get the final answer for the total power consumed by the load, which is 786.08 megawatt. And if we use conventional measurement method, which is this equation, 3 V phase I phase cos theta, and cos theta is simply substitute by the power factor, which is 0.9. So we'll get almost the same answer, which is 786.06 megawatt. So these are the results that we obtained from the calculated value and also for the simulation value, which for the simulation I will show it later. So the simulation value and the calculated value is almost the same. There is a tiny bit of differences. So based on the results, we can conclude that the value for the simulation using PSIM software is almost the same as the calculated value. So the first and the second objective for this project is successfully achieved, which is the first objective is to evaluate the parameters of the system, and we have successfully evaluated all of the parameters. For the second objective, which we want to identify whether if there's any differences between the calculated value and also the simulation value. So basically, we also have successfully achieved that objective. There is a difference between the calculated value and also the simulation value. And next, the objective is to justify the normal operating condition of the electrical system. So normally in industrial fields, most of them use a balanced three-phase condition. So our system is a balanced three-phase Y-connected system, so it is operating in its normal condition. So we look into the simulation using PSIM software, and this is the circuit which I have drawn. So let's do the simulation. And next we want to identify the parameters for I line, which is equals to I phase. Next, we get the RMS value for the current, which is 1.83, and if we add these three values, we'll get the average value. Next, we want to know the V phase A, V phase B, and V phase C as we reverted. So this is the value for the phase voltages. Next, for the line voltages, A, B, B, C, C, D. And we'll get the value 2.5, 2.57, almost the same as I get. And next, we want to know the value for the wattmeter method, which we will use the value of I1 and VAB. I1 and VAB. Let's press this. So we'll get the value 3.83 exponent of 8. And then for the second wattmeter, we use I2 and also VBC. I2, VBC. So we'll get this value. So if we add both value for wattmeter 1 and wattmeter 2, we'll get the total power and almost the same as we calculated. As a conclusion, we can conclude that all of the objectives of this project is successfully achieved, and this is all can be proved by the results obtained, which is the first and the second objective is successfully achieved, and also based on the results, we know that the value of the calculated value and the simulation value is slightly different. So we have successfully achieved the first objective and the second objective, and also the third objective, which is the system is normal. Since the voltage drop is plus minus 5%, so it is normal and okay. And that's all from me. Thank you.